Implicit differentiation is something that it kind of sounds complicated, but it's actually very quite simple. Essentially, if we take the derivative of x's, we're going to do our normal thing. But if we take the derivative of y's, then we got to tag on either a y prime or a dy dx. That's it. All right. So reminder of your derivative notation. This is like defined explicitly, like your normal stuff, y equals, and then when you do your derivative, that's y prime or dy dx, you do the derivative of y, you get your y prime or dy dx, and then you just do your normal derivatives with the x's right there, right? Even if you have this option, you're not going to want to do this option. It's going to take us too long. The implicit differentiation is going to be a quicker way than this stuff right here. Sometimes you have an equation where you don't have y by itself, and you can do algebra. You could solve it for y. You can get y in terms of x's, and then you could kind of take your normal derivative there. You won't always have that option. If you look at this problem, there's no way to get the y's by themselves, like all in terms of x's there. And even if you can, you don't want to do that. This implicit differentiation, you just basically, on an implicit differentiation problem, when it looks like this, is we don't do any solving at the beginning. We're just gonna right away start taking derivatives as is. And if we need to take derivative of y's, then we're gonna tag on a y prime. So let's just talk briefly, real quick, while we're doing the y prime. There's these little differentials. There's a whole study in college semester, some called differential equations, and you work with these differentials all over the place there, and they pop up and they have a bunch of different meanings. But you know, when you do the derivative of x squared, right, you're just going to go y prime is going to be a 2x technically, and you'll see why there's no reason for me to force you to do this. Technically, in the last several sections, I could have had you do this, where you tag on dx over dx. These letters right here always match. You're doing the derivative of that variable, and it's with respect to x, okay? So it's respect how fast the y's are changing, how fast x are changing with respect to x, and we're gonna fine tune that more in the next section when we do related rate problems, because then we're gonna do with respect to time, and it's gonna be a dy dt and a dx dt. But for now, whatever variable this is, the top letter matches. And right now in this section, we're doing everything with respect to x. So this bottom part is always gonna be a dx in this section at least. And so notice that this is just equal to 1. That's just why when you do the derivative of x's, you just do your normal derivative, okay? But here's the thing. So like if you do the derivative of y's, when you do this derivative, you're going to get a 10y. But since you're doing the derivative of y's, what you're going to tag on is a dy dx. So you're doing all these with respect to x as well. We're doing everything so far. So that's why there's an x on the bottom. And then those letters on the top are always going to match there. Now, since the y prime and the dy dx are equivalent, we can either put this down, or we can just simply write 10y, and instead of using the dy dx notation, we can just tag on the y prime. That's for this section, because everything is x's and y's this section. And the next section, when we start doing work problems with respect to time, we're going to need to put a dx dt, a dy dt, and I'll talk to you about what that actually means when we get to it. So just real quick, when we do an implicit differentiation there, like if you do the derivative of x's, that's just going to be your normal 12x squared, and then you're done. You don't need to put like the dx over dx, it's unnecessary. But if you do the derivative of 4y cubed, you're going to get a 12y squared, but you just did the derivative of y's, which means you got to tag on the y prime. So you can choose. I just think it's quicker to write the y prime versus the dy dx, so I'll do that until I get to the next section. Then I'm going to need to do stuff with respect to time right there. So we could just do a bunch of this stuff right here. So basically, you just need to remember, if you do the derivative of y is attached to it, tag on that y prime. And technically, it's always implicit differentiation, because even when you had a normal equation, you did the derivative of y, which is 1, and then we tagged on the y prime. So it's like you're always technically doing that, but you don't really think about it when you already have the y by itself. So let's do a few examples here. Let's start off with something pretty basic here. I just want to take the derivative. I want to get y prime equals something. That's it. This first example, I'm going to use the dy dx notation, and the rest of the examples, I'm only going to use the y prime notation just because that's quicker. But I just want to model for you that you could do either or. So I'm just going to take the derivative of everything as is. My goal is not to solve this for the y and then get a plus or minus stuff there and have to do two separate things there. Forget all that, all right? Just do, if you see something like this, just do the implicit differentiation there. So you're just going to go 2x, just take the derivative of everything as is. So the derivative of x squared is 2x. The derivative of y squared is a 2y. But since I did the derivative of y's, you got to tag on the y prime. And I said I was going to do the dy dx notation this time. So you just tag on that dy dx notation. And then you must also do the derivative of the right-hand side as well. The derivative of that number is equal to 0. And then we still want to find the derivative. So I need to solve this equation for that dy dx right there. So I'm going to move the 2x over. And then we're going to divide both sides by that negative 2y. So we're going to get the dy dx, which is our first derivative. Negative over negative is going to be a positive. And then you're going to get this 2x over 2y. And then that can reduce to x over y. So there's your first derivative. And if I say find the derivative at a certain point, then you got to plug that point in. Because in the last several sections, you just kind of ignored the y value. You just took the x coordinate and plugged it into your derivative because your derivative always just had x's in it. Well, now, if our derivative has x's and y's in it, you're going to need to plug in the x value and the y value. So same rules still apply. If I give you a point and say find the slope of the curve at that point, then you take those coordinates and you plug it into this first derivative. Boom, that's the slope of that curve, the slope of that tangent line. If I say write the equation of the tangent line, then once you have your point, and then once you find your slope by plugging it into the derivative, then you're going to do that point slope form like we did in a prior section as well. All right, so then let's just do a few more examples. You have to recognize the products, the quotients, the trig functions, okay? So right here, you can't just do the derivative of this, which is a 2x, and write that down, and then do the derivative of that, which is y prime, and write that down. That's wrong. This is a product right here. So you have to be very careful, recognize the product rules. Those are big deductions if you don't recognize that that's a product. So once you recognize it's a product, that's your first function, there's your second function. Let's do that product rule together. So we're going to go first function, just write it down, and then you're going to times by the derivative of the second function. So two ways you can think of that. I think the quickest way is just go, hey, when I do the derivative of y, I get a y prime. Or you could say I could do the derivative of y, I get 1, but since I did derivative of y's in it, we tag on the y prime. So there's the first function times the derivative of the second, and then we're going to go plus the second function. Don't need to tag on a y prime here because you're not taking the derivative of stuff with y's. You're just rewriting whatever that second function is. You're not doing a derivative. So we did the second function, just write it down. And now we're going to times by the derivative of the first function. So there's my product rule. That's the derivative of this term. And then this is just a normal power rule. So I'm going to do the derivative of that, which is going to be an 8y. But again, here's the implicit differentiation. That's it. You did the derivative of y's attached to it, which means you got to tag on the y prime. That's it. All right. And don't make that too complicated. And the derivative of that is going to be 0. Sometimes people bring the 3 down. You're doing the derivative of everything, including that constant, which is always 0. Now, here's a pretty typical solving thing here. Sometimes you're going to have y primes on both sides of this equation. Your goal is to move all your y primes on one side, all the other stuff on the other side, factor out and divide. So I'm going to do this. I'm going to group together my y primes on the left. So we got x squared y prime minus 8y y prime. I'm going to move this to the other side, that's negative 2xy. And then see how I got a y prime on both of those? I'm going to factor out a y prime. And you're going to do this similar solving technique on a lot of these problems here. And then you're just going to divide each side by that. And then there is your first derivative. So I'm going to make up some points here. Now, I'm not going to guarantee that the points that I'm making up are actually on that curve. I just want to do a little extension of this of a couple things that you're going to have to do. So let's just say, for example, I'm going to say find the slope of the curve. I'm going to say find the slope at a point 1, 5. And again, I just made up that point. I don't think that point is even on that curve. It doesn't satisfy that, but just for the thorough purposes, I just want to show you how to do a couple things here. Now, if you have to find the slope at that point, then you got to take the 1, plug it in for the x's. So you're going to go like negative 2 times 1, and then you're going to take the 5, plug it in for the y's, and you're just going to do basic arithmetic there. So I'm going to go 1 squared, which is 1, and then 8 times 5 is going to be 40. And so this is going to be negative 10 over negative 39. So I get 10 over 39. So that is the slope of the curve at that particular point. And it's a pretty powerful method we're learning here because you're getting a lot more complicated looking equations. And even if you can't get the y by itself in terms of x's there, you can still take the derivatives and you can still find the slopes of those various curves at those points there. And then if I now said, let's write the equation of that tangent line, you know, the directions that we've been seeing over and over again, once you have your point and your slope, then you can just do your point slope formula. So you can just go y minus your y value equals your slope. times x minus your x value. And then remember, we can leave that in point slope form. There's one other thing in this section where they're talking about a normal line, okay? And then what you want to kind of just get down to a normal line is perpendicular to the tangent line. So if I said find the slope of the tangent line, that would be the 10 over 39. If I then turned around and said, hey, what's the slope of the normal line? Then, you know, perpendicular lines have opposite reciprocals. The normal line is perpendicular to that tangent line. So if the tangent line has that slope and they're perpendicular to each other, remember, perpendicular lines have opposite reciprocals. So there's the slope of your normal line. And if I said, what's the equation of the normal line, then you're going to do the same thing. You're still going through that point, just that's your slope now instead. So then you go y minus 5 equals a negative 39 over 10 times the x minus 1 right there. So equation of a tangent line is that easy. And then normal line, you just do the opposite reciprocal and still do your point slope form. So I just want to get that in there before I forget. Okay, moving along here. I want to choose a slightly more involved example. So we're going to do this one right here that we got in purple. So this is just this guy right here we're working on. And I want to show you a very common thing that kind of students kind of mess up on this one. Actually, I'm going to give you a trick that hopefully you're not going to make that common mistake that students mess up on, all right? So I see a problem that looks like this. I'm just going to take the derivative of everything as is. That's implicit differentiation. And when I take the derivative of y's with it, I'm going to tag on the y prime. That's it. So normal derivative, I'm going to go 16x. Normal derivative, which is going to be a 4y, but since I did derivative of y's attached to it, I got to tag on to y prime. Now right here, this is like 3x times y. This is a product, which means we must apply the product rule. Now, if you treat the 3x as the first function and the y as a second function, then you're going to do the product rule. But notice that you got that minus sign right there. If you treat the 3x as the first function, you got to put the whole product rule in parentheses, carry that minus sign down and distribute that. Typically when students do that, they tend to mess that up and make sign mistakes on here. Usually the most common mistakes on these things are the sign mistakes. I'm going to give you a little tip that I think if you follow this, I think you'll be happier. And I find far less little mistakes when people approach it this way. What I would do is treat the negative 3x as your first function. So include the negative as part of your first function. Do your product rule. You won't need any parentheses. You won't need any extra step. Just do your product rule with that negative as part of your first function, and it'll be done. And it'll be done accurately if we do this right. All right, so I'm going to go product rule. I'm going to go first function. Just write that down. And then you'll times it by the derivative of the second, which is a y prime. And then we'll go plus the second function. Just write that down. And then you'll times it by the derivative of the first, and the derivative of negative 3x is a negative 3. And then the derivative of that right-hand side is equal to 0. Sometimes you might have another product rule over here, and you got a bunch of stuff over here. And if you have y primes on both sides of the equation, your goal is to get all your y primes on one side. It doesn't matter what side, either the left or the right, and get all the other terms that doesn't have a y prime attached to it on the other side. All right, so right here, I'm going to do a couple things in one step here. I'm going to group together my y primes. Actually, no, let's just do a couple steps here. So I'm going to get all my y primes on the left. Everything else I'm going to move over there to the right. So that's going to give us a positive 3y over there. And I move the 16x over there. It becomes that. And then we're just going to factor out the y prime. And then we're going to divide. And there's our derivative, and we're done. If you happen to move your y primes to the right, whereas I move mine to the left, here's the thing. If you check in answers here, if all of the signs are opposite from the answer that you're given, then it's still accurate. All right, like if you went negative plus negative, or I'm sorry, if you went negative plus plus plus, if all the signs here are opposite, that is still acceptable, because all that means is you moved your y primes to the right and I move my y primes to the left. Now, if one of the signs are off or two out of the 4 signs are off or 2 or 3 signs are off, then you did something wrong, all right? You made a mistake someplace. But if all the signs are opposite, then that's still accurate. So you know that you did that right. All right, let's do one, possibly 2 more problems. All right, I want to work in one with the trig for sure. So remember your chain rule options there. If you have the sign of something, I don't even see what that is there. I have the sign of something. This is a trig problem. So if you do the sine of an angle when you do the derivative, you're going to do cosine of that angle times it by the derivative of that angle. So we're going to do cosine of that angle, leave that angle alone, and then you times it by the derivative of that angle. So now you're pretending that's your original problem. That's x times y. Guess what? That's another product, and you got to use the product rule right here. So you're going to go first times the derivative of the second, derivative of y is y prime, plus the second times the derivative of the first, and the derivative of x is just 1. So there's my product rule, and the derivative of this side is going to be 3. Now, I'm going to show you 2 ways of how to solve this one, because sometimes you have a y over here, sometimes you don't have a y over here, and it depends. If I don't have a y over here, I can do this either way. If I do have a y over here, there's one way that you need to approach that. That's going to be the second method that I show you here. So one approach, if you had to learn one approach, I would learn, actually this is going to be this first method right here, is I'm going to go ahead and just take this cosine of xy and distribute it through that parentheses. And then at this point, if I had any y primes over here, I can move all my y primes together. I can factor out and divide like I normally do, right? But see that, so that's the real good reason for always kind of doing this approach right here. But right now you only have this one y prime right here. So I'm just gonna solve for that y prime. So I'm gonna subtract this to the other side. And I'm gonna divide both sides by the x in that cosine of xy. All right, now because it is just a number there and it's not like a 3y prime that's complicating things, or a 3y or something like that, it's complicating things, you could also solve it this way, is you can go back up to this step right here and you could divide both sides by that cosine, just because I have a number right there, because then that's going to give us this method. And then if you solve this for the y prime, you're going to subtract the y over, then you're going to divide both sides by the x. And at this point, you know you're not allowed to leave complex fractions in your final answer. So you have to look at that mini fraction right there. We're going to times the top and the bottom by this cosine of xy. That times that, those will cancel out. You're going to get 3 minus the y cosine of xy. And on the bottom, you're going to smush those bottoms together. And notice how you're creating that same exact answer right there. So this method right here, the second method, only worked because I had a number. If I would have switched this to a y prime, and then you have a y prime here and over here, this method isn't helping us at all. So I would, if you're going to learn one method, I would probably choose this method right here, because if you had a y prime right here and a y prime right here, at this point, you would move your y primes over to that side, that would be over there, and you can still factor and divide like normal. So I just want to kind of review some of the algebra things that kind of students run into when they're working out these problems. Last one, and this is more, if we break this up into a couple of days, you'll probably see this on the day 2 of this stuff, but I figured let's just do one video for all this stuff here. Okay, if you have to do a second derivative, here's what the directions are going to ask us to do on this one. It's going to say find the second derivative. That's what that notation is. But it's going to say in terms of x and y, which means you can have x's in your final answer, you can have y's in your final answer, you could have a combination of x's and y's in your final answer. What you cannot have in your final answer, you can't have a y prime or a dy dx in your final answer there. So when we're doing this second derivative problem, you need to get rid of the y prime at the end. And the same thing is true, like we're always going to get rid of the complex fractions as well. So this is an example. I already did the first part for you. I did the first derivative for you. The derivative of that is 0, and then I went straight to the product where I did first times the derivative of the second plus the second times the derivative of the first. That was just an easy derivative. Moved all my y primes to the left, factored it out, and divided. There's my first derivative. Now, if I want to find the second derivative, I know the derivative of y prime is y double prime. I'm going to do that up here. And when I do the derivative of this, guess what this is? This is a quotient, which means we need to apply the quotient rule. So let's go do that together. We're going to go denominator times it by the derivative of the numerator. The derivative of that is 0. The derivative of y is y prime. And then we're going to go minus the numerator, just write that down, times it by the derivative of the denominator, which is a -1, all over the denominator squared. Okay, now let's be careful with our signs here. Technically, you have a negative times a negative, which is just going to make that a positive. Or if you distribute the negative through and then distribute another negative through, you're just going to change the sign a couple of times there. So what I'm going to just recognize, when I have minus a negative, that's going to turn into plus a positive. And then so we just have that. And then here's the deal. So the x's and y's are okay. You have to always get rid of that y prime right there. And the way you're always going to do that, that's why I boxed this over here. This is your y prime. This is your first derivative. So you're going to take this answer and you're going to insert that for the y prime. And then sometimes it'll cancel out nicely. Sometimes you got to get rid of complex fractions. You just got to look at what you're doing there and be solid with your algebra skills that you learned in Algebra 2 and your pre-calc days. So I got the 1 minus x that'll carry down. And in place of the y prime, I'm going to plug in that first derivative. I'm taking that and plugged it in right there. So there's my numerator. And then it won't always happen like this, but on this particular problem, those binomials cancel each other out. You have 1 plus y plus 1 plus y, so it's going to be 2 plus 2y over 1 minus x quantity squared. So this is your second derivative. So you got just a couple of problems like that. Now, you remember, if it's a constant, you can factor out that 2 if you want, or you can leave that alone because it's a constant, it doesn't matter. But remember, if you have like x cubed and an x to the 5th, then you should be factoring out that x cubed and kind of going from there. A lot of times on these implicit differentiation problems, if we get GCFs and stuff involved, sometimes on stuff like this, we just gotta go ahead and just kind of leave it like that, because when ultimately when it comes time to plug stuff in, then we'll be okay. There's a couple that when we're doing some homework, I believe there's like a number 45 and a 47, that the answers might look a little bit different, but I'm going to say that a couple things here. One, when you first work it out, you're going to get this if you do it correctly, and that's going to be a perfectly acceptable answer. Also, what you notice is the answer key also has this on it. And I would like for you to think for a little bit how to get from there to there. I think if you stare at that long enough, you're going to see how that works. And we want to be exposed to that, because an AP test, sometimes they'll just leave it alone. Sometimes they will do something like that. So we're going to get exposed to both. But, you know, if I'm giving you an assessment, they would be perfectly fine to just have that answer right there. And then on 47, what you're going to get if you do that right is y squared minus x squared over y cubed. And then you can just kind of leave it like that, or you can get this answer right there and then just think about how to do that. We could talk about that later if we need to. Thank you.